So today we have Bart talking about an introduction to double string theory and non-Riemannian backgrounds.
Okay, so thank you for having me. And yeah, I'll tell you a little bit about double string theory and non-Riemannian backgrounds. So this is still very much a topic that I've just recently got interested in. So I think it's going to be today's talk is going to be aimed at a pedagogical level. There's not going to be many great insights, but my main focus will be actually this paper that you see here. It's a paper from I think almost 5 years ago now from Jong-Hyuk Park and Shigeki Tsukimoto. And I think this is a rather interesting paper because on one part, I'll show you a little toy model in bosonic string theory. And I'll show you something interesting that might happen in these non-Riemannian backgrounds. In what's different to the usual Riemannian backgrounds, at least. And always in everything that I'll be talking about today, I'll have in mind some phenomenological applications, and that's really where my interest lies in the topic. So I guess if you have never heard of these two terms, double string theory and non-Riemannian backgrounds, you don't have to worry. And at least at this point, every time I refer to a non-Riemannian background, I just want you to have in mind that the usual notion of a metric or a Riemannian metric does not exist in these spaces. So the plan for today is as follows. I'll start with some words of motivations. I will tell you why we're interested in this non-Riemannian backgrounds. The first thing will be that, in fact, in these non-Riemannian backgrounds, what happens is that in the supergravity equations of motion and action, the tachyon kinetic term is gone. In fact, I'll show you later on that the tachyon kinetic term is at least classically completely gone from the string theory, from the world sheet theory in the bosonic case. And then I'll show you some interesting applications to string phenom, at least possible applications. Then to make some of these details a bit more clear, I will briefly review double field theory, and then I'll review BRST quantization such that we can actually have a look at a simple case study. And this final fourth part of today's talk will examine a model that, a simple toy model really that Park and Sugimoto in their paper here studied, and they showed that this theory is tachyon free. Okay, so the first motivation for why we're interested in these kind of non-Riemannian spaces boils down to tachyons in string theory. So in some sense, the open string tachyon has been to some extent understood through the seminal work of Sen and many other people that followed. And the open string tachyon can be understood as an instability of the D brane on which it lives. On the other hand, the closed string tachyon is a little bit more mysterious, and such an understanding is of course missing. That's why we're talking about it. But what is known about this closed string tachyon is that you can go ahead and you can, of course, use your usual critical bosonic string theory to compute the effective Sugra equations of motion. And at the leading order, you come up with an action like the one you see here. And it has this tachyonic kinetic term. And as I'll show you in a moment, in fact, this tachyonic kinetic term is absent in non-Riemannian spaces. And I think that's one nice, cute result, and I think it might be of interest to string theorists. The next motivation that I should stress that these are also the motivations of Park and Sugimoto. These are not my own ideas, of course. I'm just summarizing their paper, really. Anyways, the next motivation, and I think this is closer to me, boils to how we can actually use these non-Riemannian spaces as spaces for compactification in the context of string phenom and maybe even beyond string phenomenology. So probably many of us know that Koza-Klein theory was originally postulated to unify GR and EM. So whether you like it or not, it has some serious, at least, drawbacks if you think about the experimental data and the particle data that we have. And the one common drawback of the very simple ideas of Koza and Klein theory, if you just compactify it on a circle, is that it gives rise to these gravy scalars. So more precisely, what I have in mind right now is this simple Einstein-Hilbert action that you see down here. and then I take the ansatz for the metricas on the right. If you plug it into the action and then compactify on the circle, you get this effective theory here, and you see that there's this sigma scalar. And the sigma scalar is a massless mode, and in fact, it acts in some sense as a fifth force. And clearly, that's not something we see in the data, and you might not like Kaluza-Klein theory for this reason, essentially. And of course, there's an entire tower of massive Kaluza-Klein modes above it, but that's a whole different story. So one thing which you might want to do if you don't like this Kaluza-Klein theory, this is ancient history in some sense by this point. But what you might do is consider a compactification on a curved space. And if we compactify our previous Einstein-Hilbert action on some sort of curved space, these gravity scalars get a potential. And this potential goes roughly like 1 over r squared of this. Let's consider an S2, so the radius of this sphere. But in fact, as you see, this potential is minimized by taking r to infinity. And so in this setup, what ends up happening is the compactified dimension gets essentially decompactified, and you're back to the higher dimensional theory. Of course, this is all too simple, and what you might want to do is include some fluxes in your compactified space, so some gauge fields. And in that sense, you might find a potential which allows for some minimum, and you might work towards giving these gravity scalars some mass. There's other things you might want to do. You might also want to consider non-perturbative corrections to these sorts of setups. And this is a very heated, I guess, topic in string theory. And there's much to say, and I'm certainly not the person to say about it, but some references, hopefully you can see them, are here from different types of people with different views. So it might be interesting to have a look at them. But one thing which is interesting about these non-Riemannian spaces, at least certain non-Riemannian spaces, is that the gravity scalars are absent completely. What I mean to say that is that in some sense, these non-Riemannian spaces are rigid and they don't allow for gravity scalars. I won't have too much to say on this, but in fact, it's a very simple result. You can see it in this paper by Cho, Morand, and Park from 2018. So in that sense, maybe it's an interesting avenue for string pheno, and because of that, I think further developing this approach of double field theory and compactifications of non-Riemannian spaces might be worthwhile. So that's pretty much all I wanted to say about the motivations of this work that Park and Sugimoto did. So I will move on now. Yeah, if you have any questions, you can stop me at any moment right now. So I wanted to now give you a brief idea of what T-duality wants to do. And I'm going to try to motivate it very quickly from in the context, say, of closed bosonic string theory. And what I want to consider is examining this closed bosonic string theory under a compactification on some circle of radius r. And what's novel in this compactification on a circle of radius r is the existence of winding modes. So unlike in this simple example which I gave you with Einstein-Hilbert, with this particle action, I mean, if you quantize it, in the case of the strings, we have winding modes. The string can wind around this compact space, and this essentially gives a new contribution to the mass condition. So what I'm writing here is in blue is the mass condition for these strings that we're examining. And what I want to point out is that there's a certain duality or symmetry in this mass spectrum, namely that if we change the radius that we're compactifying with some other radius, which is alpha prime over r, and at the same time we switch the excitation and winding numbers, in fact, the mass spectrum remains the same. And this is the source of T-duality, and this simple relation here, it even extends to interactions as well. So what this closed bosonic string theory that we're looking at actually has under compactification, it has an infinite order discrete symmetry, and it's an ODD symmetry. And it only becomes manifest under compactifications, under these toroidal spaces. But you can, in fact, extend this T-duality to more complicated spaces, but I won't say anything about that. At some point, string theorists got, I guess, in the early 1990s, maybe late 1880s, late 80s, string theorists got interested in the idea to try to sort of make this ODD symmetry manifest from the beginning, rather than having it emerge only under compactification. And this idea has been recently, actually, there has been a resurgence in trying to develop it further, especially by Park. If you go ahead and search his Inspire page, he has a lot of papers on this recently. But the idea is to, at least in this simple bosonic string theory that we're discussing right now, is to try to exchange our usual target space fields, the metric, the Kalber-Mond field, and the dilaton, instead of fields that are manifestly covariant under this ODD symmetry. So these are this generalized metric and the generalized dilaton. I'll give you some definitions for these two in a moment, but the idea is essentially to do that, to make this ODD manifest from beginning, and to write a string action. So just some bookkeeping. What we're actually doing is we're extending also the number of space-time dimensions that our theory, at least effectively, is living in. So previously, these mu-nu indices, they were d-dimensional. The mn indices are 2D-dimensional now. And also in this these ODD covariant quantities are contracted using this invariant metric here. And yeah, I want you to notice that it's off-diagonal rather than diagonal. So some defining properties, and these are essentially the only defining properties of this generalized metric and generalized dilaton, are the ones that you see here in the bottom of the blue.
Just a quick question for notation. So you have the generalized metric as h mu nu in the thing just above. Is that the same as this y mu nu? Wait, what's the?
You mean J?
So you did. Oh, J. Yes. What is is there a connection between h and J?
So H is your dynamical thing, and inside of that thing, if you consider, for example, a Riemannian space, I'll give you the parameterization of H in a moment. But if you consider a Riemannian space, H will in general depend on G and B. So the Riemannian metric and the Kalber-Mond field. On the other hand, J, it's just a constant invariant metric. It's essentially as given here. It's this off-diagonal. It's a bunch of zeros and a bunch of ones. That's it. So
I see. Yeah, like Minkowski type thing.
Yeah, but it's off-diagonal and it's just ones. Yeah, the point is that in this ODD space, you actually use this J invariant metric to contract all the different indices.
Oh, I see. Okay, that makes sense. Yeah, thank you.
Right, so you essentially have only these defining properties, and from these you should be able to figure out how you parameterize H. So I'll give you a few examples in a moment. So as I said, the space-time coordinates are also doubled, but the physics that we, of course, want to describe is d-dimensional, not 2D dimensional. I know that there's people who complain always about how string theory has additional dimensions, but we don't want to add more. We want to stick with what we have. So we still need the system to depend on d dimensions rather than 2D dimensions. And in order to enforce that, we have what's known as a section condition. And essentially, this section condition enforces that our fields should depend only on d of these space-time dimensions. And you can solve this condition here in the middle just by setting all of your fields to be independent of this x tilde. So one thing to say about this division of x tilde and x, they're a little bit like the winding modes and just the usual string modes. Of course, if you if you don't compactify your space, this X tilde doesn't really have any physical meaning, except for making your system manifestly ODD covariant. Okay, so I wanted to show you how a generic sort of rank 2 tensor looks in this ODD. This generic, how a generic ODD rank 2 tensor looks, and it's basically this A here. And I just wanted to point out that sort of the indices are in slightly different places than if than you might imagine. Okay, so I remember I said some time ago that in these completely non-Riemannian spacetimes, the tachyon kinetic term will vanish. And it's not too hard to show that right now. It's essentially straightforward. Basically, the tachyon kinetic term and in this manifestly ODD formulation will end up looking like HMN and then contracted with these partial derivatives of the tachyon field. And you go ahead and you evaluate it with this H. In this non-Riemannian spaces, the top left corner of this H will actually be 0. I'll show that in a moment. So that term vanishes, and then all the other terms, we can eliminate them just using our section condition. And basically, since our fields have to be d-dimensional, all these other terms vanish. So in essence, the tachyon kinetic term is gone. And that's a claim I was making before. I just wanted to clarify it right now. Okay. So now I want to move on to the worldsheet theory, actually, and I want to write it in a manifestly ODD manner, and we're going to use this later on when we examine this example of Park and Sugimoto. So to do that, you can essentially postulate the following action for your bosonic string theory. So the first thing to notice, the first thing that's different is, of course, instead of the usual Riemannian metric and the B field, we have this generalized metric in the kinetic term in this area part of the functional. And you should also notice that the usual worldsheet derivative is generalized to a ODD covariant derivative. And the reason for this is because the usual worldsheet derivative of the X term does not transform as an ODD vector. So we really have to gauge this X field to form an ODD vector. So that's one thing. Another thing is you should see that there's this term with the Levi-Civita symbol, and that term is essentially enforcing the section condition on our X field. Another point is, this is actually at this point, I think, already semantics, but you see that in front of the action, the prefactor is changed by a factor of 1/2 compared to the usual string action. And this is necessary if we want to rederive from this formalism the usual Riemannian worldsheet action. Okay. Right. So at this point, what I wanted to show you is how we can actually plug in this a Riemannian parametrization of this H metric back to this manifest ODD action and get back the usual Riemannian string, just so you see that it works out. So a famous parametrization is as follows. The one here, you see that there is a Riemannian metric, there's a Kapp-Ramond field, and now you can also see that if there is no Riemannian metric parametrizing our spacetime, you see that the top left corner, as I was saying earlier, just vanishes. So at this point, it's not too difficult to just plug it in and go through the calculation. And if you plug it in like I do here in the first line, and then you go ahead and you integrate out this gauge field and you fix the coordinate symmetry, you're basically back to your usual Riemannian string. So here, for simplicity, I just set b to 0, but the point I'm trying to make is that the formalism is consistent. We can get back the Riemannian string. But of course, that's not what we're ultimately interested in. We're ultimately interested in describing these non-Riemannian spaces. And in these non-Riemannian spaces, we'll have to use these some time ago, I gave you these conditions that defined the generalized metric. And we can use these conditions to parameterize the metric in terms of these matrices X bar, Y, and Y bar. Right, and this we can do that, and using those conditions, we can write the form for the generalized metric in cases where the Riemannian metric ceases to exist. So you could also include in this H here that I'm writing a Kalber-Mond field, but for the purposes of what Park and Sugimoto did, we won't really have to look at that. So this index I and I bar, they run from N and bar, as you can read on this slide, and they just sum up to D. So these X's and Y's, they're in some sense D by D matrices. Okay. So yeah, I'm not going to show you all the details, but in the moment we're going to use this action, so you can go ahead and plug this generalized metric back to the worldsheet action, and you're essentially left with this equation here in the end. And in a moment, I will show you the mass spectrum of this equation, and I will show how exactly the tachyon is gone in these non-Riemannian spaces. Okay, I think this is all I wanted to say about the double field theory aspect of today's talk before we move on. So if there's any questions, you can go ahead and ask now. Otherwise, I'll just move on. So for those of you who are familiar with BRST quantization, there's obviously nothing new that I'll say now. But for those of you who've never heard of this, never seen this, I just wanted to say a few words about this so that what we will do in the final section is not going to feel too detached. And if you want to read more about BRST quantization, you can go ahead and really grab any PhD level textbook on quantum field theory, or if you're interested in the context of string theory, you can maybe go ahead and look at section 4 in Polchinski's volume number 1. So the reason we want to consider BRST quantization is that in some sense it provides at least for the type of theories that we'll be interested in today, it provides a systematic way to quantize our theories and keep track of potential anomalies. So let me try to sketch how the process goes. I won't give you an example or anything like that, but I just want to sketch what happens. So usually when we're given an action and we have some fields, in this case, I'm denoting them by some collective coordinate phi I. I can both stand for different fields, x, psi, and so on. And in this case, it also stands for the space-time point at which they're evaluated. So the actual action and the path integral is going to have some gauge symmetries if we're interested in gauge theories, as we are. And by assumption today, these gauge transformations will have to satisfy an algebra. Essentially, you're doing 2 gauge transformations, and you get back a gauge transformation. And as is customary, if we want to deal with this gauge symmetry, what we typically do is we pick a certain gauge to simplify our calculations. But of course, a priori, we would like to show that our calculations don't really depend on the gauge that we're working on, and to do that, it's best to use BRST quantization in some sense. So I would now like to continue this schematic discussion a little bit. So say we have some theory, some gauge theory given by the action S1. It has some gauge redundancy, and we wish to fix the gauge. In order to fix the gauge, what we typically do is use a Faddeev-Popov procedure. So we try to fix this gauge dynamically. Here you see that our gauge condition was F phi equal to 0, and now in this dynamical procedure, it's essentially this gauge condition is given by the variation of S2. So that's what we're adding to our action. And then S3, we have to also add it to compensate for the fact that we're adding S2. Anyways, we can. This is a sort of standard procedure that we can use to enforce this gauge symmetry. And the essential point I want to say here is that once we add these different terms into our action, we can see that our system admits what's known as a BRST symmetry. In this case, I've decided to written schematically the symmetry as follows. You have these ghost fields, P's and C's. Depending on the system you might be interested, of course, you might have different types of ghosts. But let me continue the schematic discussion because this is not really important for what I will want to say. But what I want to say now is that let's say if we consider slightly changing our gauge fixing condition. So we started with our gauge fixing condition f phi equal to 0, and now we want to slightly change it. Of course, under such a change, our action should be our physical observables should be independent of this. So what we might want to do is look at how our correlation, a arbitrary correlation function changes under this. It's not too difficult to see that you get this first line here, essentially because S1 is already independent under this gauge symmetry. And then since S2 and S3 are linear in this F, you can also get the second equality. And then in the final equality, I essentially define the BRST charge operator. And now, since we can do any arbitrary modification to our gauge fixing condition, essentially what ends up happening is that our physical states have to be invariant under this BRST operator QB. Okay. And one other thing I should say is that we might also want to move within the space of our gauge choices. And if we want to move within the different gauge choices, our BRST operator will have to be a conserved quantity. And you can again go through a similar short derivation, and you will see that for arbitrary sort of changes in our gauge fixing condition, it will imply that the BRST operator has to be nilpotent, so the square of it is 0. In fact, you might think that, well, since the action of QB on a physical state is 0 and the square of QB is 0, then perhaps maybe it's just a constant and it just squares to 0, so it is 0. But that option is precluded. I won't really discuss that, but that's not possible. Okay, so one final thing to say about BRST quantization in this schematic discussion is that is the concept of a BRST cohomology. So for example, we might find a state to make this concept more concrete. You might consider a state which looks like this QB acting on chi. Chi does not need to be necessarily a physical state. But if we chi doesn't need to be a physical state, but of course, if we act on it with QB on the entire QB chi, it's going to vanish. So QB chi acts as a physical state. And of course, if we try to write any correlation function with either itself or any other physical state, it will have to vanish. So what I'm trying to really say here is that our physical states, they have to be identified as a certain quotient. So we can't only look at states that are annihilated by QB, but we also have to quotient by states which are null. Essentially, or I guess states that are really states that differ only by these null states. Oh, yeah, I guess I forgot to say that this QB chi kind of state is null. Okay. So hopefully, if you're interested if you want to understand that, really, you should really go check the textbooks like Pyszkowski 1. Okay. So finally, getting to the paper that I was going to talk about. So in the paper, Park and Sugimoto, they noticed that if we examine this usual closed bosonic string theory, the tachyon will be gone. And in fact, the entire theory will truncate to only a single excitation level. And let me show you how that goes through now. So some time ago, I tried to convince you that the action in this non-Riemannian space, it will take take this form. And now I'm just changing some of the variables in case you're following the paper, just to make the discussion more. And this is the same as Sparks and Sugimoto. Okay, so we use these field binds, and we also move to the light cone coordinates. And essentially, this action that I've written here, it has the usual Weil symmetry, the worldsheet diffeomorphisms, but on top of that, it also has invariance under these ODD rotations. And unlike usually, because usually it would have target space diffeomorphism also, now this worldsheet action, instead of having manifest target space diffeomorphism, it has manifest. That was before we actually. Okay, it's still manifest here. Sorry. So it has these double target space diffeomorphisms, which are manifest. Okay, so what we might want to do is fix all of these gauge symmetries to simplify our problem. In fact, there's also some other gauge symmetry, an extra gauge symmetry, I guess you could call it, is given by this equation here. So what we might want to do is fix all of these, and we can dynamically fix them using this Fateev-Popov procedure again, and the full action can be written as you see here. So at this point, what you might want to do is derive all the equations of motion of the system and find the reduced action, the reduced Lagrangian really, for the system that satisfies all of these equations of motions. So that's what Park and Sugimoto essentially do. They write this reduced action over here. And if you're familiar a little bit with string theory, it's essentially starting to look like a beta gamma system coupled to the usual DC ghost sector. But now, instead of the beta gamma system playing the role of a ghost system, it's actually coming from a physical sector. So these conjugate momenta of X's, they can be identified as the beta fields in the beta gamma system, and X can be identified as the gamma fields. But now we have actually each one of these for each of the space-time dimensions. Okay, so this is the system that we want to analyze at this point. And you can go ahead and using standard no-error procedures, you can count the BRST charge. I've not written here the full action of the BRST operator and all these different fields, but you can find it in the paper, but it's a little bit long, and I don't think it's very illuminating. But you can find it, of course, in the paper. And then using those, using that, you can construct the charge. And again, this is a sort of standard calculation. If you know the beta gamma system, you can just plug it in here, and instead of the usual one, you just have that, but number. I mean, you have d of them depending on how many space-time dimensions you have. And one thing to point out is that I've separated this BIST charge into a left-moving one and a right-moving one. And that's because, as you might see from this action here, is that you see the xi part of the string, it's in some sense completely chiral, and then the other part becomes completely anti-chiral. So it depends only on one of the light cone coordinates. So we can split it like I've done here, and then it's a simple path to quantization. There's nothing really new. You can square these BRST charge operators that I wrote, and you will see that they're only nilpotent in the case when the number of these chiral X fields is the same as the number of anti-chiral X fields. And this actually ends up implying that the critical dimension is the usual 26-dimensional one. So you need 13 chiral and 13 anti-chiral dimensions. So then the final thing I think I want to stop after I explain this is that you might go ahead and want to construct your mass spectrum, and you can simply do that by writing your L0 mode, and that L0 mode has to annihilate all your physical states. And now, since there's really no, in some sense, no kinetic term, essentially once you go ahead and do the calculation, it just ends up being these number operators, and beta and gamma and b and c and the normal ordering constant. And unlike in the usual string theory where you would have a mass term sitting somewhere here, so that you would have many different solutions to this equation, you essentially have only one possible solution depending on the normal ordering constant A. Which implies that the spectrum is possibly truncated to only one level, and then you can in fact go ahead and compute this this normal ordering constant. It's again just the usual string calculation. You can find it in Pyszkowski, and you end up finding that the only level that survives this truncation is in some sense the first excited level, and all the other states are killed by L0. Yeah, so I think this is this interesting result of this Park Sugimoto paper that I wanted to tell you about today. I don't think it has an immediate application to string phenomenology, but I think this non-Riemannian compactifications are an interesting alternative to traditional compactifications, and hopefully at least this much I was able to convey today. So with that said, that's all I wanted to say today. So if you have any questions, I'm happy to try to answer them. Otherwise, thank you for having me.
Great. Thank you very much for the very nice talk. So I guess questions.
I have one small one. Bartosz.
Sure.
Previously you mentioned like QB of chi is physical. Chi
Sure.
is,
Yeah.
even though chi is non-physical, QB of chi is physical. But I also remember you mentioning QB of chi is null. So what's going on? Is there some mistake?
No. So this QB chi is both, right? What I mean to say is that you can construct a state which looks physical. It is annihilated by QB, right? Let me maybe write something. Right, so this is a standard discussion, and if I have not explained it well, I strongly suggest you look at, I don't know, chapter 4.3 in Pyszkowski, volume 1. But oh, sorry, let's see. So what I want to say is that you have this guy, because you act on it with QB, because this is 0, you know this is 0 because in a consistent theory, Q squared has to be 0, right? So you know that this guy is going to be 0. So you're going to call this guy physical. But now the thing is that you can add this guy to any other physical state, and if you try and compute any correlation function, it makes no difference whether you have that guy or not. So in fact, he's both physical and null.
I see.
It's just a definition thing, and yeah, I suggest you have a look at the textbooks. There might be other things I missed. Yeah, okay.
I missed the start of the talk, so perhaps you mentioned this, but could you say more about what do you mean by non-Riemannian in this context? So you're talking about, say, Riemannian, like the theory is defined on Riemannian manifolds or something like that as being Riemannian. And then what do you mean by non-Riemannian? Do you just mean there isn't a Riemannian manifold or something more specific?
Yeah, thank you for the question. I should have been more precise. So the obvious answer is exactly what you said. I have in mind spaces where you cannot define the Riemannian metric G. Basically, that's all. But if that's the only thing that I meant, then the question would be, how do I describe these non-Riemannian spaces, right? And the only way I know how to describe them is using this framework of double field theory. So I guess what I really mean by non-Riemannian is that originally you had this generalized metric which looked like this. In our non-Riemannian spaces, the top left corner will have to vanish, and then we'll try to find a condition for H, which satisfies that, and this is what I mean by non-Riemannian spaces.
Do you ever say specific like example for non-Riemannian space? I'm just trying to think.
Essentially, I have in mind a manifold. In this case, it's just flat, and it is parameterized. I mean, and the metric, you have this H here. I don't have anything more precise except this flat example here.
Yeah, that's okay. Thanks. Yeah, I'm just trying to think. Yeah, I had another question about how it is set up okay. I was trying to formulate a question, but let me just think about it a bit more. I'll come back to you in a second.
Sure. So one thing maybe, yeah?
You go ahead.
Sorry. Yeah, I just wanted to add that, of course, this discussion today was completely about the bosonic string. And one thing that I'm interested actually right now is trying to sort of reinterpret this in superstring theory. So I'm trying to find the worldsheet action right here. So trying to find a worldsheet generalization of something like this action to superstrings. In fact, well, first of all, why is that interesting? Well, it's interesting because we might want to apply this sort of framework to string pheno and actually construct some models that connect to string pheno and see what is actually new about these non-Riemannian compactifications in comparison to more traditional things. And one thing I wanted to say is that if you're familiar with string theory a little bit more, the Green-Schwarz formulation of this of the superstrings in this ODD manifest manner, in fact, is known. But I guess one problem that's open is it's not a very difficult problem, but it would be to write down the RNS formulation, which is manifest ODD, and essentially that would be nicest because RNS is much simpler than GS. Okay, yeah, I wanted to add that before I forget.
Oh, I remember what my question was. So the results you have at the end is for the double field theory construction. And I'm just thinking about how it is sort of being generalized for other non-Riemannian setups. So is like the double field theory, correct me if I'm wrong, but the double field theory is one setup to do non-Riemannian string theory. But what about other setups?
I know that you can connect this I know that you can connect this double field theory to something like Gomez-Oguri string, and but I don't know if this result here that I wrote applies to Gomez-Oguri. I don't think it does. But as for the truncation, I can't tell. But I know that you can match this double field theory approach to other non-Riemannian strings, so that's possible. But in some sense, this non-Riemannian approach is also, I think, a little bit distinct because it's not like you're taking a limit where you're taking the metric to vanish and somehow your quantities remain well-defined because you have some, like in the Gomez-Oguri, you maybe have some Cabramont background field, which is adjusted in such a way that everything is well-defined. But in this double field theory approach, you simply say there is no metric. Metric's gone, and can I describe the geometry? And it ends up you can, using this generalized metric. So yeah, I recommend you see this Park Sugimoto paper because there's some discussion there on how you can actually, I don't know, map this to the Gomez-Oguri string. But as far as the spectrum is concerned, I think it's distinct.
I see. Yeah, that makes sense. Thank you.
maybe a similar sort of question. So I guess this generalized metric thing is like quite nice actually, because people think about it in terms of generalized geometries and G structures and stuff like that. Do you know if there's anything interesting? Because I suppose this corresponds to an ODD, the metric here. I know people also consider like exceptional and the
Right.
exceptional group instead. Do you know if there's anything interesting related to this construction, maybe by considering exceptional geometries instead?
I think it would be possible to do. I think the framework is developed enough to do something like this, but I can't tell you. I can't give you a precise answer if that's what you're asking, but I think it should be possible.
Yeah,
Yeah.
no worries. It's a bit of a a tough question, I suppose. I mean, I
Yeah,
don't
but
know too much
I
about this
think yeah,
area.
yeah, I think if you're interested in this and you simply search for a string which is manifestly covariant with respect to these exceptional symmetries, of course not all of them, but some of them has been constructed, and for some of them you can probably redo this analysis and yeah, that's my answer essentially. The result of this analysis, I can't tell you.
Mhm. Thank you.
I have a question not related to talk, but somewhat tangentially related. Um, you mentioned before that you're working on holography type things. Is there a connection between the stuff you presented today and that, or are these two separate, like, different research directions?
Well, I think maybe it's a speculative question, so
Yeah, that's fair.
I'm not sure how I should answer, but
Okay, that's fine. That's fine. That's fine. Yeah. Thank you.
yeah, I think there might be interesting connections, but it's you know there's not much on that yet, and yeah, if you have
Not yet. Yeah.
any ideas,
It's
then
fine.
you can let me know. But
No, I'm just putting two nouns together, seeing whatever they mash together to be, but it could just be nonsense. It's fine. But thanks.
okay.
Do we have any final questions?
Maybe another speculative question. Where do you see the direction of this area of research going? Do you have any um, particular
Well,
opinions about it, or?
I'm impressed that this is a subject I recently got interested in. I want to learn more about the subject, so I decided to give this seminar as an opportunity. But personally, if what got me interested in this is trying to actually construct some interesting superstring phenome models using these non-Riemannian compactifications. And I think as a physicist, that's what interests me in this. So trying to construct a model that is phenomenologically interesting, but starts off from this non-Riemannian compactification. I think that's an interesting direction.
True. Yeah, thanks for that. That's good.
Okay, well, maybe we can wrap up here then. Yeah, thank you very much for this very, very interesting talk. It was very nice.
Yeah, thank you.